Alright, so in this video we're going to talk about the properties of definite integrals as well as do an example 4. So the first one is if we switch your limits of integration, if a's here and b's there, these are just numbers, right, for our limits, right? I'll get some color on there. See, we switched them. If you switch your limits of integration, what you need to do is you need to multiply by a -1. And remember that your definite integral is that limit of a Riemann sum. That little tiny change in x is your b minus a all over n, which is also minus an a minus b all over n. There's the -1 showing up there as a factor if you change those limits of integration. Here, if your limits are the same, you're looking at the area under a curve as x goes from a to a. That's no area at all. 0. Right? There's no area here. The integral of a constant, c is just a constant, is going to be c times b minus a. Oh, on this one I didn't type an equal sign. And if we look at that one graphically, say here's your c. Y is always c, y is always 2, y is always 10, right? Here's y is always c. Going from x equals a to b, what does this definite integral represent? It represents the area under that constant function. Y is always c, bound by these vertical lines. X is a, and x is b. What's the base of that rectangle? The base is b minus a. What's the height of this rectangle? It's c. All right. This is really delightful. The integral of a sum of two functions, we can integrate, we can think about the area under f on its own, and then think about the area under g on its own. And what do? We go ahead and add those two areas together. This picture out of our textbook I really like. Let's zoom in. Here's the area under f. That. The area under g is all this. You want the area under f plus g? That they just take the area under g and then they add on the area under f. What they're showing you here with those vertical lines is that this area right there is the same as this area. Not a proof, but some compelling visual evidence. Similarly, the integral of a difference, we've got a subtraction sign right here. I can think about the area under f on its own. Then I can think about the area under g on its own and do what? Take the difference of those two areas. Constant multiple rule. This is similar to differentiation, right? The derivative of a constant times a function is the constant times the derivative of the function. Same thing here with integrals. This is c times the integral from a to b of f of x dx, right? essentially I can take the function f and multiply it by c, stretching it vertically by that factor of c, and go find the area under that curve as x goes from a to b. Or I can just think about the area under f as x goes from a to b and then multiply by c. It is important with all of these here, your a, b, and c, those are numbers. The x is a variable, right? The f's and g's are our functions. Okay? All right. A couple more properties here. So here, if a is less than c, that's less than b. So let's see that here. A, c, b. A, c, b. You have a choice. You could go ahead and find the area under f as x goes from a to c, and then go find the area under f as x goes from c to b and add them two together. And when you add those two areas together, notice that you'll get the area under the curve f as x goes all the way from a to b. So we can write it like this. Integrating from a to c and then integrating from c to b is the same as just integrating from a to b. We need to pay attention to the order of these numbers, right? A is less than c. C is less than b. Right? And I think that visual aid does a really good job convincing us that we can either choose to write this integral as one integral, or sometimes it's nice to go backwards and expand it out. Right? And our last one, this one is going to come up for us in a proof of the fundamental theorem of calculus. Let's just talk about it visually. So notice here that this area, this rectangle, that area is the length, or here, the base here, it's b minus a, times the height, m, b minus a, times that little m. That area, I think I do want some color on here. We'll leave it. That area is less than this area. Would we agree? That area is the integral as x goes from a to b of f of x dx, which is less than or equal to the area of this big rectangle. Yeah, and the area of that big rectangle is its base times its height. Its height is big M, and the base is your b minus a. All right, so I just had an idea for visualization. Here's this guy. Oops. Right? This area is your b minus a times your little m. Scooch that up a little. All right. The area of your big rectangle just do that. Good enough. Is right here. It's a big capital M. And here is your b minus a. We have a continuous function on a closed bounded interval, the extreme value theorem says that this function will have a minimum y value, function value, and an absolute min and an absolute max, right? That's what those little m's and m's are. Okay, so here are some properties of integrals. Don't stress about this one so much. I want to just illustrate a few common mistakes, and then we're going to go ahead and do example 4, and that'll conclude this video. So this is used a ton in your Calc 2. We can compartmentalize our thinking when we have addition and subtraction. Just like I can differentiate across terms, I can integrate across terms, but not factors. We can't integrate across multiplication or division. This is not true. Times g of x. Man, would it be nice if this were true. This is not equal to, go find the area of under the curve f and then multiply it by the area under g. Big time no. Okay, it will happen to you in your Calc 2, but that's pretty common. Same thing with division. I can't compartmentalize my thinking. I can't just think about the integral of f and the integral of g separately and then just divide them. That's garbage. But it is understandable that students will do that when they're new. Can't just think about the area under f, the area under g separately, and then do a division of them. That's not true. Okay? All right, one quick example, and that'll conclude our lesson. So, if it is known that the integral from 0 to 8 of f of x dx is 12, in other words, we know the area under the curve f as x goes from 0 to 8 is 12, and we know the integral as x goes from 0 to 5 of f of x dx is 8. In other words, the area under f as x goes from 0 to 5 is 8. Then we're asked to find this value, the integral as x goes from 5 to 8 of f of x dx. All right? In other words, we're asked to find the area under f bound by the vertical lines x is 5 and x is 8. Now you can approach this graphically or analytically. I'm going to go ahead and do them both. We know that the area under f as x goes from 0, we need a 0, we need a 5, and we need an 8 there, right? I'm just going to make up a little sketch. Here's our f of x. We know the area under the curve from 0 to 8 is 12. In other words, I know that this whole area in blue is 12. 12. We also know, another quick sketch, right? We also know that the area under the curve from 0 to 5 is 8. So that means we know that this is 8. And then the question is, well, what's the area under the curve from 5 to 8? All right. Well, if the whole thing is 12 and this part is 8, this part has got to be 12 minus 8. In other words, it's 4. Okay? You could also approach this analytically using really this property right here. We could say, hey, I know that integrating from 0 to 5, the area from 0 to 5, plus the area from 5 to 8, has got to be the area from 0 to 8. And we were given this one to be 8. We were asked to find this one, and we were given that this one is 12, right? So you could also approach it that way by just saying 8 plus what is 12. Okay, so without drawing a picture, you could also answer this question. Now, there is one last problem, a think, pair, share, and I'm going to leave it to you. And again, this is prep for the written part of the final. Might be on there, might not. And it's a little bit more involved than the one that we just did. You can approach it either from a graphical standpoint or from an analytic standpoint. I will give you one little hint. It is easier to think about these areas when the lower bound down here is the smaller number, and the upper bound in that limit of integration is the larger number. And I want you to just notice that -1 is actually bigger than -2. So you may want to switch these limits of integration, but you have to go and use a property. If you switch the limits of integration, what do? Okay? In our next lesson, we will be doing fundamental theorem of calculus. Thank you guys for all your patience with COVID. This is entirely optional, but it's a simple little activity, kind of reflecting back on example 1 that lays some of the foundation for part of the fundamental theorem of calculus. And if you choose to do it, that's great. Okay? Thank you guys for watching.